Oh.
Got it.
Is it on?
Mm-hmm.
Yeah.
How good are you?
Very big.
You know how to zoom and everything?
Yeah.
Those little arrows. Okay, we are on page 7, 0.2. We're going to talk about the Earth's motion around the sun. We know that the Earth spins like this, right? Do you know how often it goes around in a day? Once every day, right?
Once in a little bit.
Not really. What was that?
Once in a little bit.
Did you read ahead, or did you already know that?
No, that's why
That's
there's
why we
daylight
have
savings
daylight
and
savings.
like the switch every 4 years.
Oh, okay. Well,
Oh,
I thought you were thinking of something else. A day, if you think about a day as the time it takes for the sun to be right overhead, or as high as it can possibly get. If you think about it, the Earth spins around, and now the Earth is back to the point where it originally started, right? If the sun is overhead. And let me get a little pin. You can see this a little better. I've put that pin on St. Simon's Island. Okay? So, in 24 hours, right, the sun's right straight overhead again. So that's a day, right? But we have to factor something else into it.
You should be walking around too.
The Earth is also going around like this.
Oh.
And it goes around one time every year. So there's two things happening here. The Earth is spinning and it's moving this way. But it's spinning a lot faster than it's going around this way. As far as it spins around 365 times for every time it orbits once. Right? And it's actually, what you're talking about, Eliza, it's 365.25 times it spins around for every time it orbits once. So, if you think about it, here's the sun. Here we are on St. Simon's, and the sun is directly overhead. And then it spins around, and it's moving this way a bit. And so it actually has to do a little bit more than a single rotation to get back to the sun being right overhead. You see what I'm saying? Let me start here again. I'm exaggerating the amount that the Earth moves this way. But the sun's directly overhead, and my tack is pointed straight that way, right? And so the Earth turns and moves, and now the tack is pointed straight that way again, right? So it's been around one full rotation, but it's not yet pointed at the sun. It has to go a little bit extra than one rotation to be back at the sun again. So a full day where the sun goes from noon to noon the next day, where the sun is at its highest point each day, is a single rotation and a little bit extra. And so, they show this in the book on page 8. Here we are, here's point A, here's the Earth pointed right at the sun. And after what we call it a sidereal day. A sidereal day is a full turn of the Earth. But we're not yet pointed back at the sun. It has to turn a little bit extra turn to be pointed back at the sun again. We call it a solar day. The full turn and a little bit extra that's needed to point back at the sun again, due to the fact that the Earth has moved from here to there. So a solar day is a little bit more than a single rotation. A sidereal day is just a single rotation. It goes back to where you started. Does that make sense? Ask me to explain, those of you who don't understand. or have any sort of question?
Why did we do that?
Because of the extra distance that the Earth has to move. Okay? If the Earth, this is a good point, if the Earth was still, if it wasn't orbiting, then just a single turn would be a day. One single turn would be a day. But since the Earth has moved this much, you got to turn a little bit extra to have the sun straight overhead again. Make sense?
Every day be a sidereal day?
Well, a sidereal day is just a single full turn, and actually, a single full turn would put the sun a little bit lower than it would be if you didn't do the extra turn. So a sidereal day is shorter than a solar day.
How long do you have a sidereal day?
Every day. A sidereal day lasts, I keep losing this thing. Whoops. A sidereal day is 3.9 minutes shorter than a solar day. A solar day is 24 hours. We have defined a solar day as being 24 hours. So a sidereal day is 23 hours, 56.1 minutes. So you do a solar day has to have a little extra spin in it to get the sun back exactly overhead. Does that make sense, or have I totally lost y'all?
The solar day is back to direct sunlight. But
A solar day is back to the sun directly overhead.
Right.
So every day you're standing there and the sun goes down. Do you know why the sun goes down? It's not because the sun is moving. It's because the earth is turned. So we call noon the sun's highest point. In other words, the sun's highest point in the sky. If I was standing here where this what is this called? Where this tack is, the sun would be at its highest point there. And then, as the earth turns, then we have dusk, where the sun's right at the horizon. And then if the earth turns a little more, now it's dark. It's nighttime. And then, as it turns around again, here we have the sun. It's pointing this way. Here's where you're standing. The sun is just rising. And then now the sun is directly overhead. And now the sun starts to set. You see what I'm saying? So at noon, when you're just facing the sun exactly, that's when the sun is high, its highest point in the sky. So from noon one day to noon the next day is when the sun is at its highest point in the sky.
But the sun will be at a 4-minute degree difference than the day before. Right?
Yes, if you were just to do a single turn of the earth, the sun wouldn't be at its highest point the next day. You have to turn a little bit extra to get the sun at its highest point each day. So 24 hours is a single turn of the earth plus a little extra turn. That's 24 hours. We call that a solar day. A sidereal day is if you were watching the stars in the distance, way off. The stars in the distance are so far away that if you were just watching the stars, a single turn of the earth, here we are, I'll get over here, watching the stars, some far point away, pretend the sun is over there. If it turns around once, exactly once, the star will be back to the same point it was in the sky the day before. The extra turn puts the star in a different location as it was the night before. So a sidereal means star. A day measured by the stars is 3.9 minutes shorter than a day measured by the sun. And that's because we're going in this circle around the sun. We're orbiting the sun. The earth is orbiting the sun.
Is it the same day, though, or is each day sidereal and solar day?
We use the term day, we use to refer to a solar day. Because we're only worried about the position of the sun. So when we say a day, we're talking about all the way around and a little bit more. That's our 24-hour day. A sidereal day is not quite 24 hours because it's all the way around, and then we stop there for a sidereal day, and it's actually another 3 minutes to go to get to the solar day. I don't know. Read it tonight. See if you can process it. Sidereal versus solar day, kind of interesting. So for us, a day means from noon to noon, and that's a little turn and a little bit extra. Okay, let's move on. Okay, another thing we have to think about is the sun appears to change positions in the sky as the Earth orbits. Now, so think about this. There's a bunch of stars in the background. When the Earth is here, it appears that the sun is at a certain location compared to the stars in the background. As the Earth orbits, the sun appears to shift compared to the stars in the background. And so if you go a whole year, this is a whole year, the sun is now in front of those stars that are way out there. If you go 6 months later, from the Earth, the sun is in front of those stars in the background over there. See, the sun appears to shift position in the sky over the course of a year. In the ancient peoples, they knew the sky really well. They knew what stars were over here and what stars were over here, and they had named them in the constellations, right? For instance, the star over here, the star pattern, might be, what's somebody's favorite? Give me your sign.
Scorpio.
Scorpio. Okay, Scorpio is a good one because I know what that looks like in the sky. Scorpio is a star formation that looks like this. It's a bunch of stars kind of in that pattern. Have you ever seen Scorpio? And what year is that you were born, Scorpio?
94.
94. Now what month? What month? November, okay. So in November, the sun appears to be in Scorpio. And what that means is, what that means is the Earth, if the sun is right here, the Earth is about right here. And if you're standing on the Earth looking towards Scorpio, the freaking sun is in the way. And you can't even see Scorpio because the sun's so bright. It's in the middle of the daytime. You can't see stars in the daytime. So the ancients said, oh, the sun is in Scorpio. Scorpio is special. But guess what? 2 months later, or 6 months later, let's say, when the Earth is over here, you can see Scorpio. At night, you can see Scorpio. Scorpio's back here. Oh, I see there's Scorpio. And the sun is instead blocking a different constellation. And there's a whole chart of this. Here's the chart. Here's the Earth orbiting the sun. And you see September, there's September where the Earth is, there's December where the Earth is. So in November, right about here, the sun is in Scorpio. There's Scorpio. And that's how they get the signs, all the signs of the zodiac. The signs of the zodiac are what the sun is blocking during that particular month. So in March, the sun is blocking Pisces, this thing that they thought looked like a fish in the sky. And in June, the sun is blocking Gemini. So the best time to see Gemini is in December, 6 months later, when the Earth is on the other side, so at night you can look out in the stars and see Gemini. That's what the zodiac signs are. It's the constellation that the sun appears to be in. And there's only 12 zodiac signs because there's a lot of other constellations. There's a lot of other constellations out there that the sun doesn't go through. The sun only goes through a select 12 constellations. All the other 76 constellations are in other directions and the sun never goes in them. So if you're thinking about a celestial sphere, the sun moves along a line on the celestial sphere as the Earth, and the sun's not really moving, it's the Earth that's moving. The Earth is going around the sun. But the ancients didn't know that. The ancients thought the Earth was still and the sun was moving. They had no way to know that the Earth was moving. They couldn't feel it moving, so they figured it wasn't moving. Isn't that cool?
How fast does it rotate? And move in orbit.
How fast does it rotate?
And move in orbit.
Well, it rotates through a 24,000 mile circumference in about 24 hours. So it's about 1,000 miles an hour. It's spinning.
Wow.
It spins through about 1,000 miles on the equator in an hour. How fast does it orbit? 1,000,000 miles a day. Which I don't know how many miles an hour that is. What's 1,000,000 divided by 24?
Oh.
Anybody got a calculator?
Miles per second.
40,000 miles an hour?
Dear.
40,000 miles an hour. So that's going pretty fast. Now you have to remember the sun is also moving. And so
Wait, how fast is the speed of light again?
180,000 miles a second. Fast. Okay, so we call this path that the sun seems to take in the sky along the celestial sphere over the course of the year. The sun switches places along the celestial sphere and appears in different constellations. We call the path of the sun around the celestial sphere the ecliptic. The ecliptic. See that word there? The ecliptic. That's the path of the sun along the celestial sphere over the course of the year. And it's due to the Earth's movement, but the ancients didn't know that. So the stars, through one night, the stars moved as the Earth spins, but the sun slowly shifts position to different locations over the course of an entire year. Isn't this neat? It's the coolest thing y'all have ever seen. Come on.
The sun would be inside that, wouldn't it?
The sun would be on the surface of this.
Then how would it block a certain constellation if it was on the surface?
Because it's so bright wherever it is, you can't see that area. You see what I'm saying?
Mm-hmm.
You can't see any of the stars really at night and in the daytime. So the sun's so bright wherever it is, pretty much half the sky is blocked out. But it's centered at a certain point. And the ancients were smart enough they could figure that out. Well, the sun's over here. We can see this whole part of the sky at night. And the sun's over here. It must be in this constellation.
Okay.
Does that make sense? Those ancients are pretty... See, they didn't have any TV. We wouldn't have figured any of this out because we'd be watching TV. But all they had to do was watch the skies.
Should we write those down?
What? This information? Yeah, I'm about to talk about it. There's something else called the seasons. Have you ever heard of the seasons before? Winter, fall, summer, spring. Huh? Why do the seasons exist? Well, it's simply because the Earth is tilted. The Earth isn't straight up and down, it's tilted. So as the Earth goes around the sun, sometimes we're in the northern hemisphere. The northern hemisphere is tilted toward the sun. That's summer. But when you get on the other side of the sun, the northern hemisphere is tilted away from the sun. That's winter. So if you're tilted away from the sun, this part's going to be colder than this part. This part's going to be hot. So in December and January, this is the formation it takes. The sun, and I have it extra tilted just to make the point. But the southern hemisphere is in summer in December and January. If you think it's too cold in the winter, just get in a plane and fly to Australia. It'll be summer there. Their summer is in December and January. So their Christmas is in the middle of the summer. It's 105 degrees Christmas. They're dreaming of a white Christmas, but they ain't getting it. So you go to the summer now, and it's real hot. You go, oh, it's hot. Fly to Australia. It's freezing there in July. Isn't that different? And it's all because the Earth is tilted. If the Earth was straight up and down, you wouldn't have any seasons. Because it wouldn't matter where you are, you're always the same distance from the sun. The only reason we have seasons is because of the tilt of the Earth. The Earth is tilted at 23.5 degrees. So there's a slight tilt, a 23-degree tilt off of center. 23 degrees if you had a what's the thing that measures a protractor, if you could imagine a 23-degree angle from straight up and down. It's not much, but it's some. 45 degrees would be a real good tilt, and 90 degrees would be on our side. Did you know Uranus is tilted at 90 degrees almost? Uranus has almost a 90-degree tilt. Uranus, like your butt. No, you've never heard that term. We use it a lot in astronomy. It's actually pronounced Uranus, but we like to say Uranus because it's funny. Okay, anyway, so there are certain times of the year we call them the solstice. The summer solstice is when the sun is as high as possible in the sky. That's the point at which the northern hemisphere is most tilted toward the sun. That would be this point. The summer solstice occurs every year on June 21st. It's the longest day of the year because we're tilted so much toward the sun that it stays daylight for a longer time. So that's for the northern hemisphere, it's the longest day of the year. For the southern hemisphere, it's the shortest day of the year. There's not much time where, if you're in the southern hemisphere, where you can even see the sun on June 21st. 6 months later, December 21st, that's our shortest day of the year in the northern hemisphere and the longest day of the year in the southern hemisphere. December 21st. If you live at the North Pole or up in Alaska above the Arctic Circle,
Night all the time.
and it's around June 21st, the longest day of the year, guess what? The sun never sets. It doesn't. Imagine standing right up here at the North Pole here. It doesn't matter how it spins, the sun never sets. You're always pointed toward it. We call it the Arctic Circle, the area where the sun is up at some point of the year, 24 hours. If you go below the Arctic Circle, the sun at least sets every day. Well, at least a little bit. Isn't that interesting? That's why we have this Arctic Circle here. That's the point at which, at some time in the year, the sun doesn't set. Of course, when you go to winter, and now you're on the North Pole, the sun never rises. It's dark all the time. And you'll have, up here in the Arctic Circle, you'll have a good 6 months of darkness, especially if you're near the North Pole. Santa Claus, he's dark all the time in the winter. They never show that, do they? They never show the elves running around with flashlights. That's what they'd be doing in the winter. All those cartoons are lying to you. They can't see anything. There better be headlights on that sleigh, or he's not going to know where to land. Y'all. Anyway, so what's exactly in between June 21st and December 21st? What do we call that? Exactly in the middle between them.
Equinox.
We call that the equinox. The equinox is the time where the northern hemisphere isn't far from the sun and it's not close to the sun. It's right in between. At the equinox, day and night are exactly even. They're both 12 hours. That's why they call it the equinox. It occurs every year on September 21st and March 21st. That's when there's equal amounts of day and night in the northern and southern hemispheres. So September 21st is called the autumnal equinox, and March 21st is called the vernal equinox. So that's at this point in the orbit and at this point in the orbit. It's exactly 90 degrees to the summer and winter solstice. We call that the equinox. Well, so if you look on the celestial sphere looks like this. The sun seems to move. The sun seems to get high in the sky at the summer solstice and low in the sky at the winter solstice. And again, the sun isn't actually moving, the earth is moving, but it's from the earth it seems that the sun is moving. So what do we call this path along which the sun moves around the celestial sphere? The ecliptic. No cross country. So the sun seems to be highest in the sky at the summer solstice. And you'll notice, if you ever tracked it, in the summer, the sun gets real high up in the sky. It's not quite directly overhead, but it's real high up. But in the winter, it never gets very high. It's always pretty low in the sky. Have you ever noticed such? Probably not. Yeah. You might be too busy watching TV and stuff to notice this.
As with all the planets of the solar system, Earth revolves around the Sun. Each orbit takes a year, shorter than Mars and the outer planets, longer than the two innermost. Imagine a line extending from Earth through the Sun to the background stars. During the year, as Earth orbits the Sun, so the stellar backdrop changes. We can't see the stars, of course, because the Sun's so bright. But if we could, this is the path the Sun would appear to take from May to September. Astronomers call the line the ecliptic. Looking in the opposite direction, in the evening this would be our view, a view that shifts from night to night. Season by season, the change is obvious. But over 24 hours, the shift is almost imperceptible, because the stars rise and set just 4 minutes earlier each day. In 3 months, a shift of 6 hours. Again, looking toward the Sun, remember it's our annual orbit of the Sun that causes its apparent journey along the ecliptic. The stars through which it passes are the constellations of the zodiac. The ancients saw them as heavenly figures. Taurus, the bull; Gemini, the twins; Cancer, the crab; and Leo, Virgo the Virgin. Then Libra, the Balance or Scales, and Scorpius, the Scorpion. Ophiuchus, the Serpent Bearer, is ignored by astrologers, adding an extra constellation to the 12 used in horoscopes. Next, Sagittarius, the Archer, Capricornus, the Sea Goat, and Aquarius, the Water Bearer. In the fourth and final season, Pisces, the Fishes, Aries, the Ram, and Taurus, the Bull, where we started this cycle. The 12 signs of the zodiac used by astrologers have little in common with the 13 zodiacal constellations of modern astronomy. Astronomy is science. Astrology is not.
Huh. That make it any easier to understand?
What did they ignore?
They ignore Ophiuchus,
Why?
the Serpent Bearer. I don't know. That just wasn't one of the constellations. One of the zodiac that they. The old folks used to use that, and then it got dropped. I don't know why. So this is what I talked about with the vernal equinox and the autumnal equinox and the winter solstice and the summer solstice. I want to show you about precession, though. There's one more thing. I have to skip some of these videos. The Earth doesn't always keep it. The Earth keeps its 23 degrees tilt, but it doesn't always point its northern. The axis of the Earth isn't always pointed in the same place. And I'll show you what I mean by that. Have you ever spun a top? This is a gyroscope. This was a toy that I had when I was a kid, and I remember playing with it.
The same one?
No, I bought some new ones because I don't know what I did with mine. But it's pretty cool. A gyroscope is just like a top. It spins real fast. And I'll spin it for you. And there it spins. And I want you to watch it. Turn the light on so we can see it a little better. There it's spinning. And
Of course, that's your phone.
you'll see it start to do a little thing. It kind of models precession. In just a bit here. Can y'all see it? Yeah, where you can see it. You can stand up. Here we have is you start to get a little wobble once it slows down a bit. See it wobbling a bit? Pretty amazing, isn't it? How fast it can go. All missiles have their. Oh, there was a wobble. Oh, it fell down. It starts when you see a top. Will start to do this. It'll be spinning, but it'll also be wobbling a little bit. It actually does it a little bit better. Let me do that one more time. I'm going to put it on this little pedestal that they included with the toy. Try this one more time here. You can sit it on a pedestal. See the little wobble it does there? See how the northern axis, the up axis isn't pointed in the same place? It's kind of wobbling about. Pretty cool, isn't it? It's amazing that it can do that. It will eventually stop. The Earth does the same thing. imagine this Earth is spinning like a top, and there's a little wobble that it does. It goes in a circle. And it takes 26,000 years to do one circle. So the Earth, as it's spinning, is also kind of wobbling like this. And it took scientists a long time to figure out that this was happening at all, but it has to happen. All spinning objects do this. And it turns its axis right now is pointed at the North Star, Polaris. There's Polaris right there. But if you fast forward another 8,000 years, it'll be pointed at this point in the sky. And if you go 16,000 years into the future, it'll be pointed at Vega, which is a different star. And so it does this great loop over 26,000 years. Right now it's pointed around almost at Polaris, but later it's going to be pointed at Deneb. It'll be real near Deneb in 10,000 years, and in 16,000 years it'll be real near Vega. And then it'll come back around, it'll be right at Thuban, this star, that's part of the Draco constellation. And in another 23,000 years, it'll be back pointed to Polaris, or 26,000 years. So it does a 26,000 year loop. The northern celestial pole is what it's pointing at. And we call that whole phenomenon precession. 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 So actually, in 1 AD, the birth of Christ, Polaris wasn't even being pointed at. That wasn't actually true north. It was a little bit off. Interesting stuff. Read about it. You read 0.2 tonight. It talks about all this stuff I talked about. And I guess